it's probably me.
Yeah.
So I'm crying on the inside. Bullying is not a laughing matter, though, for real. Sometimes I feel like I have to say stuff like that as everyone just laughs. God. You guys do not help sometimes. Like, I try to keep a straight face and be serious for a second. It's not working. Okay. No, it's true. I mean, I'm a nerd. We're all nerds here. Bullying is real, so like it's like a legit thing. So like we'll leave it at that and we'll move on. There's another GIF in this lecture, so we'll lighten the mood. It'll be great. Okay. First order systems and transient response. So remember, we're going to specifically look at first and second order system responses, transient responses, because they're going to compose higher order system responses. And so they're very interesting, and their characteristics show up again and again. Also, there are a lot of first order and second order systems, or at least systems that in some operating regime can be approximated as such. First order systems have input-output differential equations of the form, this equation, 1.2. So we've continued to use this B notation for the coefficients of the forcing function, the right-hand side of the differential equation. But on the left-hand side, since it's a first-order system, we like to write it with a different constant structure, a coefficient structure. We like to write it with this coefficient out front of the time derivative and 1 as the coefficient of the y term. And this is just standard, so I don't even really want to justify it. It's just, this is just a standard convention. With the time constant tau. So we call this the time constant of the system, and it characterizes the system. The time constant is one of the ways that we would characterize, or actually the primary way we characterize a first order system is by its time constant. It kind of tells us, in a sense, everything we needed to know about the system. So let's expand on that a little bit. Systems with a single energy storage element, such as those with electrical or thermal capacitance, can be modeled as first order. So just to give you an idea, but a lot of systems can be modeled as first order. The characteristic equation yields a single root. Okay, so remember from your differential equations class, you can construct a characteristic equation in order to form the homogeneous solution. And no, a prerequisite in my class often means exactly that. We're hopping right into the middle. Homogeneous solution here. Does anybody know it off the top of their heads? It's an easy one.
You set the input, just use the input, right? You would set that equal to 0.
Yeah, so you set all, so for the homogeneous solution, you set all of this equal to 0, right? So there's an exponential here. It's e to the lambda t, right? But lambda is negative 1 over tau, so we usually write negative t over tau. And then what's out front? Something. Yeah, a constant. So I'm going to use kappa for a constant. Yeah. So that's the homogeneous solution. Pretty easy to get the homogeneous solution of a first order system. And we could actually just integrate, but yeah. In any case, if you're confused on how we got there, you should definitely start reviewing that, because I'm just going to assume we know how to do that in this class. So, okay. Now we can talk about the free response. So the free response, which we typically denote y sub fr, because the other type of response is forced response, which also starts with an f. Damn it. So I thought about using phi for the free response, because it sort of sounds the same. It's a homophone. So I was going to say y phi for free response and yf for forced response. But then I was like, no, that's overthinking it. Just use 2 letters. So the free response will have FR for free of a system. So it is defined as its response to initial conditions and no forcing. So the forcing function is set to 0. So that is essentially the homogeneous solution with initial condition being applied to it directly. So it's useful for 2 reasons. 1, perturbations of the system from equilibrium result in free response. Okay, so if it's at some equilibrium and the system gets perturbed a little bit. I mean, a pendulum's a nice system to think about because we all have some intuition on it. It's like a little gust of wind came by and knocked your pendulum a little bit to the side. It's going to then respond in free response from that. So that is what we're trying to find here. That's why it's interesting in the physical sense, is it's how the system responds to some perturbation. And every real system has perturbations from equilibrium. And then the second reason is that from superposition, the free response can be added to a forced response to find the specific response. So this is another aspect of superposition. If you put in one input and you put in another input, you get those 2 responses. If you wanted to know what happened if you put both inputs in, you sum the outputs. Similarly, initial conditions work the same way. The response of the system to a certain initial condition and a certain input, you can find separately and then sum up the responses to get the response to the initial condition and the forcing. So that's what this is saying here, where YFO is the forced response. This allows us to use tables of solutions like table 1.1 to construct solutions for systems with non-zero initial conditions with forcing. And so 1.1 is on the next page, and we're going to talk more about it in a moment. The free response is found by applying initial conditions to the homogeneous solution. With initial condition y of 0 equal y0, so this is just like some constant, like 7, the free response is y naught e to the negative t over tau. We can tell this matches the initial condition. If we plug in time equals 0, it's e to the 0, which is 1. Y of 0 equals y naught, which is our initial condition, so it's correct. So what this does is it starts out at y naught and it decays exponentially to 0. So if you perturb a first order system from equilibrium, it will decay back to its equilibrium value, its 0 value. Okay, that's the free response. Let's talk about the step response. Because step is the most important one, we're gonna take a moment to talk about the step, and then we'll have a table that summarizes the others. So if we consider the common situation that B1 equals 0, so B1 being this coefficient, which is to say this term is 0. This is a common situation. In the table, we'll actually take into account when B1 is not equal to 0, so that's important. But we'll look for a moment at this common situation where B1 is equal to 0, and the input is a scaled unit step. So where k is some value like 4. I don't know, 7 and 4 just seem right today. So the solution to the equation for this step input and 0 initial conditions is y forced of t equals not 0 initial conditions. This is the general solution. K B0 e to the minus t over tau plus k B0. So this is the general case. What I said down here was that B1 equals 0. So I did take into account B1 equals 0. So that is correct. So this is steady state. This is just a constant, right? Steady. And this is the transient response because it decays to 0. A plot of the step response is shown in figure 1.2. as with the free response, within 5 time constants, the transient response is within 1% of the final value. So if we have ourselves a forcing function that's just a unit step that's scaled, and we started out at an initial condition, and we put in a step input, we get this decaying to a steady state value. Transient response is happening in here. We say approximately, at this point, it's steady, and we say it's steady state thereafter. Now, the response of all three to all three singularity inputs are included in table 1.1. These can be combined with the free response of equation 1.3 using superposition. Results can be described as bitchin', which I have a GIF for that, but I want to talk about the table for a moment. So in your text, you have not this kind of weird characters coming in. I did not fix this bug over the break. But essentially, it gives you the characteristic response in this column, which is what you get out if you put in the corresponding input, like a Dirac delta input. You get this as the output. If you put this in as the forcing function, you get this as the characteristic response. If you want to know what happens if you put that in as the input and not the forcing function, this is the total forced response in this table. So we're going to be able to use superposition to just construct solutions without having to do all the work. That's why we do this, kind of because we're lazy, but also because it's, wait for it. Are you guys fans of Stranger Things?
I haven't seen it.
Love it. Anyways, this is the best part. So sorry, spoiler alert.